Welcome to another episode. Before we begin, I'd love to know something simple about you. Where are you listening from tonight? And what time is it there as you press play? You can leave it in the comments. It's always beautiful to see how many different places and hours of the world gather quietly here. And if you'd like to join again for more nights of drifting through science and story, you're warmly invited to subscribe. Now, let's turn to something small, familiar, and quietly extraordinary. The candle. A stick of wax with a wick. Something we've all lit at one point. For a birthday, for a dinner, for comfort when the power goes out. And yet within that tiny flame lives an entire universe of science. Nearly 2 centuries ago, the great scientist Michael Faraday chose the candle as the subject of his most famous lectures. With its glow, he revealed the hidden laws of chemistry, the invisible dance of gases, and the poetry of light itself. It is the story of how the simplest things can open the widest doors to wonder. So, if you're ready, let's begin with the flame of a candle. From the very beginning of human history, fire has held us in its glow. It is one of the oldest companions of our species, a presence that gave us warmth, protection, cooked food, and a sense of safety against the dark. Before the walls of cities and the structures of science, there was firelight dancing in caves, casting shadows that may have been the first moving pictures ever seen. To sit near a flame was to feel alive, to feel at home, and to wonder. And out of this long history, the candle became a refined, portable piece of fire. A flame that could be carried in the hand, placed at the center of a table, or kept vigil in the corner of a temple. It condensed the primal vastness of fire into a small, steady glow, gentle enough to study, bright enough to guide. The candle, in its simplicity, is more than just a stick of wax. It is an object layered with meaning. In every culture that has used them, candles have symbolized warmth, life, and continuity. A candle burning at a bedside was a prayer. A candle carried in procession was a symbol of unity. Candles have illuminated sacred spaces, churches, synagogues, shrines, where their light was not just practical, but spiritual, connecting the earthly with the divine. And they have been used in celebrations across the world, the flickering flames atop birthday cakes, lit and extinguished with wishes whispered into smoke. But beyond symbolism, the candle was also a piece of technology. Before the rise of gas lamps and electricity, candles were a necessity for daily life. Made of tallow, beeswax, or later paraffin, they were a household tool, and yet one that drew endless fascination. Unlike the steady glow of a lamp, a candle flame dances. It responds to the smallest currents of air, bends and stretches, threatens to vanish with a breath, only to relight with the faintest touch of fire. A candle flame is alive in a way that feels almost human. Scientists noticed this long before modern chemistry could explain it. The flame has distinct parts: a dark core where the wax vaporizes, a luminous middle where glowing carbon particles radiate yellow light, and an invisible outer sheath where complete combustion burns hot and blue. To the naked eye, it is a simple glow. To the trained mind, it is a whole laboratory of physics and chemistry contained in miniature. The candle is therefore both ordinary and extraordinary. Ordinary because it sat on every dinner table, every study desk, every altar for centuries. Extraordinary because within it, nature reveals its deepest processes, the transformation of matter, the movement of heat, the consumption of oxygen, the birth of carbon dioxide and water vapor, even the nature of light itself. When Michael Faraday chose the candle as the subject of his Christmas lectures in 1860, he did so precisely because of this duality. He could have spoken about electricity or magnets, or his own great discoveries in electromagnetism. Instead, he chose something every child in his audience already knew: a candle. He wanted to show that within the familiar, within the most ordinary of objects, lies a doorway into wonder. that science is not separate from daily life, but written into it. This is why the candle has remained such a compelling symbol for knowledge. Think of the phrase, to shed light. It means to explain, to clarify. To hold a candle to something is to illuminate it, to make it visible. The flicker of a flame became a metaphor for ideas themselves, fragile, easily extinguished, but capable of spreading rapidly, one wick lighting another, until a room, a city, a world is full of brightness. Even in language, candles linger as symbols. Burning the candle at both ends reflects human exhaustion and yet also human ambition. A candle in the wind is an image of fragility. To light a candle rather than curse the darkness is to choose hope, discovery, persistence. Scientifically, a candle is also a lesson in transformation. Solid wax is drawn upward by the wick, liquefying into a pool and then vaporizing into invisible gas. It is that invisible vapor, not the solid wax itself, that burns. The flame, in truth, is a dance of gases, hydrocarbons breaking apart, combining with oxygen, releasing heat and light. The candle quietly demonstrates conservation of mass and energy. Nothing disappears. The wax becomes heat, water vapor, carbon dioxide. Matter rearranges itself. For the curious mind, a candle is proof that the universe hides its secrets in plain sight. You don't need a vast laboratory to discover chemistry. You need only a candle, a glass to trap its gases, a mirror to reflect its light, a breath to extinguish it, and watch the smoke carry flammable vapor that can reignite at a distance. The candle is a universe in miniature. Philosophically, it also touches something deeper. In a single flame, we see transience. The candle is always disappearing as it burns, giving of itself to create light. Its life is consumption, and yet through that consumption, it gives warmth and illumination. Perhaps that is why humans have always seen the flame as more than physics. It mirrors our own lives, brief, flickering, fragile, but capable of brilliance. And so, as we imagine Faraday's audience, young Victorians in crowded lecture halls, watching intently as the scientist held up a candle and declared it his subject, we too begin to see the flame differently. Not as background, not as decoration, but as revelation. The candle is a teacher. Its smoke is a lesson in the states of matter. Its flame is a lesson in energy. Its light is a lesson in the electromagnetic spectrum. And its warmth is a reminder that even the most abstract science begins with something profoundly human, our need for fire, for warmth, for light against the dark. It is in this way that the candle, so simple and so small, carries within it entire worlds of chemistry, of physics, of philosophy. To study a candle is to study the relationship between humanity and nature, between observation and discovery. And that is why, more than 160 years after Faraday spoke of it, the candle flame still glows not just on the table, but in the imagination of science itself. Michael Faraday's story is often told as one of the most inspiring in the history of science. Born in 1791 in Newington Butts, a poor neighbourhood of London, Faraday grew up far from the privilege and polish that often shaped the scientific elite of his time. His father was a blacksmith, frequently ill and struggling to provide. Michael himself had little formal schooling. He learned to read and write, but his world was not one of libraries or laboratories. It was one of hard work and meagre means. At the age of 14, he was apprenticed to a bookbinder. It might have seemed a modest trade, but in that workshop, surrounded by the scent of leather and glue, Faraday discovered something extraordinary. Books. He devoured them. Not novels or poetry at first, but volumes of science, encyclopedias, treatises on chemistry and electricity, accounts of natural philosophy. He read and copied out passages by hand into notebooks, sketching diagrams, summarizing experiments. The binding shop became his university, the volumes on its shelves his professors. Among those books, one in particular lit his imagination. Conversations on Chemistry by Jane Marcet, a popular science writer who explained the complexities of chemistry in simple dialogue form. Faraday later credited her work as the foundation of his scientific awakening. Through her words, the invisible became visible, gases, reactions, and forces that shaped the world. His curiosity grew restless. He began performing small experiments in the back room of the shop, winding coils, sparking wires, playing with chemicals when he could afford them. His notes reveal not just interest, but obsession. He wanted to see nature directly, not just read about it. In 1812, when he was 20, Faraday scraped together the money to attend lectures by Humphrey Davy, the brilliant chemist of the Royal Institution. Davy was a celebrity of his age, famous for his discoveries of chemical elements and for his dazzling public lectures, where explosions, flashes, and fountains of sparks thrilled fashionable London audiences. Faraday sat in the gallery, scribbling notes furiously. He later bound these notes into a book and sent them to Davy, along with a request for employment. At first, Davy dismissed him, but fortune shifted. A laboratory assistant at the Royal Institution was dismissed for misconduct, and Faraday was offered the position. From there, his life changed. He began at the lowest rank, cleaning, preparing apparatus, fetching supplies. But he absorbed knowledge like a sponge. Soon he was conducting his own experiments, and in time he became Davy's successor. Faraday would go on to discover electromagnetic induction, lay the groundwork for electric motors and transformers, and isolate important gases like benzene. He became one of the greatest experimentalists in history. Yet despite his towering achievements, he always remained modest, gentle, and deeply devoted to teaching. He never forgot that his own path to science began not in privilege, but in curiosity and wonder. This devotion to teaching found its home in the Royal Institution's Christmas lectures. Founded in 1825, the lectures were designed to bring science to young audiences, presented each December to a crowd of children and families. They became a beloved tradition in Victorian Britain, blending spectacle with education. Scientists of the institution would reveal the wonders of physics, chemistry, and biology in ways that were theatrical yet deeply informative. Faraday delivered many such lectures over his career, but none became more famous than his series of 1860 to 1861, The Chemical History of a Candle. Standing before rows of children in their holiday best, he held up a simple candle and declared, "There is not a law under which any part of this universe is governed which does not come into play and is not touched upon in these phenomena." It was a bold claim. How could such a simple object embody the laws of the universe? But Faraday was a master communicator. He showed that the flame's behavior could reveal chemical reactions, physical principles, even philosophical insights. The candle became his gateway to the entire science of combustion. His approach was patient and methodical. He did not leap to advanced concepts. Instead, he started with what the children already knew: the look of a flame, the melting of wax, the flicker in a draft. Then, step by step, he led them deeper. He demonstrated that the solid wax melted into liquid, which then traveled up the wick. He showed that the flame was not burning the solid wax, but the invisible vapor it produced. He revealed how the flame consumed oxygen from the air and released carbon dioxide and water vapor. Each lecture was filled with small experiments: trapping gases in glass tubes, relighting a candle by touching a flame to its trail of smoke, showing how a flame could be inverted under certain conditions. These were not tricks, they were insights. Each one turned the invisible into something visible, something the children could see with their own eyes. Faraday believed deeply in the power of direct experience. He once said, "The lecturer should give the audience full reason to believe that all his powers have been exerted for their pleasure and instruction." He saw science not as a list of facts, but as a living conversation with nature. His candle lectures embodied that philosophy perfectly. To understand why these lectures resonated so deeply, we have to step into the world of Victorian Britain. This was an age of industry and steam, of gas lights spreading across cities, of scientific discovery woven into the fabric of daily life. Electricity was still a mystery, chemistry was rapidly advancing, and physics was redefining the cosmos. The Victorians were hungry for science. Public lectures drew enormous audiences. Scientific societies flourished. Newspapers reported new discoveries as eagerly as political news. There was a sense that knowledge was not just for scholars, but for everyone, for workers, for children, for families gathered in lecture halls. Faraday's candle lectures fit this moment perfectly. They captured the Victorian fascination with light, both literal and metaphorical. The flame was at once a symbol of domestic life, industry, and enlightenment. In an age when coal smoke darkened skies and gas lamps glowed in city streets, a candle was still familiar, intimate, and magical. The beauty of Faraday's approach was that it showed how science lived within the ordinary. He did not need rare chemicals or complex machines to teach profound lessons. A candle was enough. And in that choice lay a democratic spirit. Science was for everyone, because wonder belonged to everyone. When the lectures were published as a book in 1861, The Chemical History of a Candle became one of the most widely read science texts of the century. It has never gone out of print. Generations of readers, young and old, have seen in its pages how curiosity can transform the simplest object into a universe of knowledge. To this day, the Royal Institution continues the Christmas lectures, broadcast on television, carrying forward the tradition Faraday helped shape. And often, his candle is remembered, a reminder that the flame of curiosity once lit spreads without end. When you look at a candle flame, it seems so simple, a teardrop of light, wavering but steady, giving warmth and glow. But if you look closer, you realize that it is not one thing at all. It is a layered, structured, dynamic process. A candle flame is like a living system, each part performing its role in a delicate balance of physics and chemistry. Faraday delighted in showing his audience that the flame was not uniform, but stratified. At its very center, right above the wick, lies a small dark core. This region is cooler than the rest of the flame, a place where solid wax has melted and vaporized, but not yet ignited. The dark core is full of hydrocarbons in vapor form, drawn upward from the molten pool at the base of the wick. These molecules are the fuel, chains of carbon and hydrogen atoms broken free from the solid wax. Surrounding this dark core is the bright, luminous body of the flame. Here, the vaporized wax molecules begin to decompose under heat. Hydrocarbons split into smaller fragments, reacting with the oxygen of the surrounding air. Not all of these reactions complete. Some carbon atoms remain, clustering into tiny incandescent particles, glowing a brilliant yellow as they reach high temperatures. This is the zone we usually notice, the golden radiance that makes a candle flame so comforting. Beyond this bright region lies a faint, almost invisible sheath, the outer edge of the flame. Here, combustion is most complete. The flame's blue fringe, often hard to see in daylight, reveals the presence of fully oxidized carbon and hydrogen. Water vapor and carbon dioxide form here, invisible but real, drifting away with the heat into the surrounding air. In this outermost layer, the flame burns cleanly, leaving no smoke. Faraday emphasized this structure again and again because it showed that a flame was not chaos, but order. Within that flicker were zones of fuel supply, incomplete reaction, and final combustion. The candle was a tiny laboratory, demonstrating the principles of chemistry with every breath of its glow. The chemistry itself is remarkable for its simplicity. Candle wax is composed of long-chain hydrocarbons, often around C25H52, though the precise formula varies. In the solid state, these molecules are locked together, forming the familiar white pillar of wax. As the wick burns, it draws molten wax upward by capillary action. At the tip, the heat vaporizes the liquid into gaseous hydrocarbons. These molecules then encounter oxygen from the air, and combustion begins. But within the flame, the process is far from instantaneous. Hydrocarbons break apart, intermediate species form. Carbon monoxide, hydrogen gas, even free radicals that exist only fleetingly. Some reactions release energy, which feeds the flame, while others wait for the right collision of molecules. The flame is a dance, a chain of events so fast and so interwoven that it appears as a single steady glow. One of Faraday's favorite demonstrations was the inverted flame experiment. He would take a candle, place a glass chimney over it, and then introduce another wick from above. The result? A flame burning upside down, as wax vapor from below was drawn upward to ignite the wick above. To his young audience, this seemed magical, a flame where no flame should be. But it was simply the vapor, invisible yet essential, rising and catching fire again. It was proof that the candle did not burn the solid wax, but the vaporized hydrocarbon. Candles also reveal subtler behaviors. Flames flicker because of instability in the supply of oxygen. A draft of air pushes the flame sideways, stretching it, thinning one side and thickening another. The flow of hot gases becomes turbulent, and the flame dances. This flicker, so familiar and hypnotic, is actually a visible sign of fluid dynamics, convection currents, and the delicate balance of combustion. When a flame smokes, it is because the balance has tipped, too little oxygen or too much fuel, and the combustion becomes incomplete. Carbon particles escape unburned, rising as black soot. If you hold a cold spoon above a candle flame, soot will deposit, leaving a dark smudge. Faraday used this to show his audience that the flame was producing matter, not simply consuming it. And sometimes the flame extinguishes itself. If melted wax floods the wick, oxygen cannot reach it. If a glass chimney encloses the flame completely, the oxygen is consumed and the flame dies. In both cases, the candle teaches a principle. Fire requires three things: fuel, heat, and oxygen. Remove anyone, and the flame vanishes. This fire triangle is now a standard of fire science, but its clearest demonstration is still a candle on a table. The candle also serves as a perfect model for studying gas laws and combustion. As wax vaporizes and burns, it expands, producing gases that rise with heat. Convection currents draw in fresh air at the base, while heated gases flow upward. The flame thus becomes self-sustaining, creating its own airflow. This is why a candle can burn in still air without suffocating itself. The hot gases drive circulation. Faraday demonstrated that the gases produced, carbon dioxide and water vapor, could be captured and measured. By placing a glass bell over a candle, he showed how water condensed on the sides and how lime water turned milky when exposed to the trapped gas, revealing carbon dioxide. In these simple experiments lay the seeds of modern environmental chemistry. The candle, he argued, was a microcosm of the processes that powered engines, factories, even life itself. To children, this was a revelation. Something as ordinary as a candle could reveal invisible gases, explain why lungs needed air, and show how matter transformed. To us today, it still holds wonder. We live surrounded by complex technologies, but the candle remains a reminder that profound lessons can come from the simplest tools. A candle flame is fragile, and yet in its fragility lies its power as a teaching device. It can be extinguished with a whisper of breath, yet in that breath lies a whole story. Oxygen rushing in, carbon dioxide rushing out, the balance of combustion tipped in an instant. The candle teaches humility. Nature is powerful, but it is also subtle. And so, when Faraday lifted his candle before a hall of young Victorians, he was not showing them a parlour trick. He was revealing a universe contained in an inch of wax and a thread of wick. The flame was a text, and he was teaching them how to read it. When Michael Faraday lifted a candle before his audience, he wasn't satisfied with just describing what the eye could see. He believed science was about doing, about testing, demonstrating, and allowing nature to speak for itself through experiment. And in the candle, he found endless opportunities for such revelations. At the heart of his demonstrations was wax itself. Candle wax, whether made from tallow, beeswax, or paraffin, is a hydrocarbon, a compound built of carbon and hydrogen. In the candle's life cycle, wax undergoes a remarkable sequence of transformations. It begins as a solid, firm, and opaque, yet under the influence of heat, it melts into a clear liquid. From there, it rises up the wick, drawn by capillary action. Finally, it vaporizes into a gas, and it is this invisible vapor, not the solid wax, that feeds the flame. Faraday delighted in showing this sequence. He explained to his young listeners that in every flame, the true fuel is not the wax you see, but the vapor you cannot. To prove it, he would take a glass tube and place it sideways into the flame, drawing off the invisible vapor. When he held a second flame near the other end of the tube, it ignited at once, proof that what burned was not the solid wax, but the vaporized hydrocarbon molecules drifting upward. This simple trick turned an everyday candle into a mystery unraveled, the unseen vapor revealed as the flame's lifeblood. One of his most charming experiments was the relighting of a candle by its smoke. Extinguish a candle, and for a moment a trail of white vapor rises, a plume of unburned wax particles still suspended in the air. Bring a lit match near that trail, and the flame leaps back down, reigniting the wick as if by magic. Children gasped, but Faraday explained it patiently. The vapor still contained fuel, and fire, like a traveler following a path, rushed down to where it had left off. In that simple act, he demonstrated continuity, the idea that combustion does not abruptly end, but lingers, waiting to begin again. Faraday also used glass chimneys to control and expose the flame's behavior. A candle placed under a tall chimney burned with a steady brightness, shielded from drafts. But place a glass vessel over a candle without ventilation, and another lesson appears. The flame dims and dies. The reason, Faraday showed, is that air is not uniform. It is composed of parts, and one of those parts, oxygen, is essential for combustion. Once the oxygen inside the glass is consumed, the flame can no longer live. To make this visible, Faraday turned to water displacement experiments. He placed a candle inside a shallow dish of water, covered it with a glass bell jar, and let the flame burn. As the candle consumed oxygen, the flame eventually went out. Then the audience watched as water rose inside the jar, partially filling the empty space. The explanation was striking. The candle had used up part of the air, transforming oxygen into something else, carbon dioxide and water vapor, gases with different properties. The rising water made the invisible visible. He went further, capturing the products of combustion to show what a candle really produced. Hold a cold metal plate above a flame and droplets of water collect, proof that hydrogen in the wax combines with oxygen to form water vapor. Bubble the exhaust through lime water, and it turns milky, evidence of carbon dioxide, the product of carbon atoms joining with oxygen. These were not just demonstrations. They were revelations about the very composition of matter. Through these simple setups, Faraday was teaching his audience the law of conservation of matter. Nothing vanishes in the flame. The wax does not disappear. It is transformed. Carbon and hydrogen atoms do not perish. They reorganize, joining with oxygen to create new substances. This was a profound concept in the 1860s, a time when chemistry was still building its foundations. For children in the lecture hall, it was unforgettable. The idea that every puff of smoke, every bead of condensation was matter continuing its eternal cycle. The experiments also hinted at conservation of energy, an idea gaining traction in Faraday's time. The flame gave off heat and light, but these were not conjured from nothing. They were the energy locked within chemical bonds, released as those bonds rearranged. This principle, though Faraday never framed it in modern thermodynamic terms, connected the candle to the engines of the Industrial Revolution, where coal and steam powered factories and railways. What burned in the candle was the same fundamental process driving the machinery of the age. In fact, the candle's flame could be seen as a tiny model of those engines. Hydrocarbon fuel met oxygen, producing heat and expanding gases. In a locomotive, that expansion drove pistons. In a candle, it drove convection currents, drawing fresh oxygen in at the base, sustaining the flame. The analogy was clear. Whether in steel cylinders or fragile wicks, the laws of combustion ruled. The beauty of Faraday's approach was its accessibility. These were not grand, expensive experiments. Anyone with a candle, a glass, a dish of water, and a little patience could reproduce them at home. This democratization of science was part of his genius. He showed that the universe did not hide its laws in elite laboratories, but wrote them into every flame, every breath of air. These candle experiments also connected to broader discoveries. Antoine Lavoisier, the great French chemist of the late 18th century, had used combustion to prove the existence of oxygen and to establish the law of conservation of mass. His experiments with candles and burning metals overturned the old theory of phlogiston and set chemistry on modern foundations. Faraday's lectures carried that torch forward, turning complex chemistry into lessons a child could see in a flickering flame. And beyond chemistry, the lessons of the candle hinted at thermodynamics, the study of energy transformations. James Joule, a contemporary of Faraday, was measuring how mechanical work converted into heat, laying groundwork for the first law of thermodynamics. The candle flame, in its way, illustrated the same law. Chemical energy became heat and light, never lost, only changed. Through wax, smoke, and water, Faraday revealed the invisible economy of nature. Every atom accounted for, every joule transformed. To watch his demonstrations was to see the world as a network of conservation, balance, and transformation. A candle was no longer just a candle. It was a lens through which to glimpse the machinery of the universe. And perhaps that is why his audiences, young and old, remembered these experiments so vividly. They did not just learn facts, they saw principles. They saw that even the most ordinary objects could speak the language of science if only one learned to listen. Today, when we imagine a scientific laboratory, we see benches lined with glassware, humming instruments, and burners powered by gas or electricity. A flame is something controlled, precise, adjustable, at a twist of a knob. But for centuries before such conveniences, the scientist's laboratory was lit, and often powered, by the glow of candles. Before the invention of the Bunsen burner in the mid-19th century, the candle was the primary flame available for experiments. It was modest, but reliable. With a candle, an alchemist could heat a small crucible, melt a metal, or distill a liquid drop by drop. Its light was steady enough to guide observation, and its flame was hot enough at close quarters to initiate countless reactions. The candle was both illumination and instrument, a partner in discovery. In the dim workshops of medieval alchemists, candlelight flickered on glass retorts and copper alembics. Alchemy, that curious mixture of mysticism and early chemistry, depended on flame to drive transformations. Substances were heated, purified, or decomposed under candle flames. The quest for the philosopher's stone, however misguided, was conducted under the same gentle glow. Without the candle, there could be no laboratory, for how else to pierce the darkness of the medieval night? Even in the early modern era, when chemistry began to separate itself from alchemy, the candle remained indispensable. Robert Boyle, the 17th century English natural philosopher, often called the father of chemistry, described experiments on combustion and respiration in which candles played a central role. In his famous air pump experiments, he placed a lit candle inside a glass chamber, pumped the air out, and watched it flicker and die. From this, he showed that air was not empty but essential for both flame and life. Candles also served as crude but effective heating devices. Place a vessel over the flame, and a reaction might proceed. Hold a needle or a mineral in the fire, and it might glow or change color. These were the earliest flame tests, precursors to the systematic methods later developed in analytical chemistry. Alchemists and chemists noticed that certain salts, when sprinkled into a flame, gave off colored light. Copper produced green, sodium a bright yellow, strontium a crimson red. By observing a candle flame, they were unknowingly glimpsing the signatures of atomic spectra. What we now analyze with spectrometers was once first noticed by the naked eye over a candle's glow. The candle was also crucial for early microscopy and optics. The first microscopes of the 17th century, built by pioneers like Antony van Leeuwenhoek and Robert Hooke, depended on strong point sources of light. A candle placed behind a lens or reflected by a mirror illuminated tiny worlds otherwise hidden. Under candlelight, Leeuwenhoek first described animalcules, bacteria and protozoa swimming in drops of water. Hooke drew the intricate structures of fleas and plant cells. Without the steady flame of a candle, many of these first glimpses into the microscopic universe would have remained in darkness. Candles even shaped astronomy in subtle ways. In early observatories, delicate optical instruments were aligned and calibrated by candlelight. Experimenters studying refraction, diffraction, or the behavior of lenses used candles as their test lights. The candle was a manageable, repeatable source of illumination long before electric lamps existed. Yet, as the 18th and 19th centuries unfolded, the world of laboratories began to change. Candles gave way to brighter, more controllable flames. The introduction of oil lamps and then gas lighting provided steadier illumination. Scientists could work at night with greater clarity, and their experiments no longer depended on the fragile life of a candle flame. The great leap came in the 1850s, when Robert Bunsen and Peter de Saga developed the Bunsen burner. Fed by coal gas and designed with adjustable air inlets, it produced a hot, clean, nearly invisible flame. Unlike a candle, whose luminous yellow came from glowing carbon particles, the Bunsen flame was blue, steady, and nearly smokeless, ideal for heating glassware without contamination. The burner quickly became the universal tool of the laboratory, replacing candles and oil lamps. But even as science advanced into this era of precision, the candle remained. It was no longer the main tool of the chemist, but it endured as a teaching device. The Bunsen burner was efficient, but it was also abstract, requiring gas lines and fittings not found in every home. The candle, however, was universal. Anyone could obtain one, light it, and reproduce the same lessons that Lavoisier, Boyle, or Faraday had drawn from it. It is worth pausing to notice how much was discovered with such a humble tool. Alchemists using candles stumbled upon flame colors that hinted at the quantum nature of atoms. Boyle, with candle-in-jar experiments, laid the groundwork for modern gas laws. Lavoisier, using careful balances and candle combustion, overturned centuries of mistaken theory and established the conservation of mass. Faraday, with nothing more elaborate than candles and glassware, introduced generations of children to the chemistry of the atmosphere. This is the paradox of science. Sometimes the simplest tools reveal the deepest truths. A candle, which costs almost nothing, can teach the principle of oxygen's necessity, the cycle of matter, the conversion of energy, and the nature of light. It can illuminate the microbial world through a microscope, reveal the structure of spectra through its flame, and demonstrate the physics of convection and buoyancy. In its flicker is both simplicity and profundity. The transition from candles to gas and then to electric light transformed laboratories into brighter, cleaner, more controlled spaces. And yet something was lost in the process. The intimacy of working by candlelight, the sense that discovery could begin with nothing more than wax and wick. In a way, modern laboratories owe their foundations to those centuries of candlelit inquiry. Think of a young alchemist in a stone chamber, candlelight glinting on glass and metal, puzzling over the transformation of substances. Think of Robert Hooke sketching a flea by flickering flame. Think of Lavoisier weighing water formed from a candle's combustion, overturning the old idea of phlogiston. Each of them held a candle, not just as a source of light, but as a scientific instrument. And so, while the Bunsen burner may have outshone it, the candle never lost its symbolic power. It reminds us that science does not always require elaborate machinery. Sometimes, all it takes is a flame in the dark, a curious mind, and the patience to watch closely. A candle flame is fragile. It bends to the faintest breath, it gutters in draughts, it consumes itself as it shines. And yet, within that fragility lies its power as a symbol. Humanity has always seen more than fire in its glow. The candle has stood for life, for memory, for knowledge, and for hope. Faraday understood this better than most. By choosing a candle for his lectures, he was doing more than teaching combustion. He was reminding his audience that science does not live only in laboratories and equations. It lives in the ordinary, in the common objects we overlook every day. He believed that wonder begins not in complexity, but in curiosity, in asking why a flame flickers, why smoke rises, why wax vanishes and yet does not disappear. In that sense, the candle is not only a scientific tool, but a metaphor for discovery itself. Each flame begins small, tentative, barely alive, but once fed with air, it grows, steadies, and radiates. Knowledge is the same. A question sparks, a thought smoulders, and with oxygen, with patience, observation, and imagination, it grows into illumination. Science, like flame, spreads from one mind to another, a torch passed down generations. This was why Faraday's candle lectures linger in memory more than a century and a half later. They embodied his conviction that science is not only for the scholar, but for everyone, for the child in the gallery, the craftsman, the curious mind sitting at home by candlelight. His message was simple. The universe hides its laws in plain sight, and the flame of a candle can teach them if you are willing to look closely. The candle also offers a lesson in humility. It consumes itself to give light, a reminder that knowledge often comes at the cost of time, energy, even life. Yet in that consumption there is beauty. The wax disappears, but not into nothing. It becomes warmth, water vapor, carbon dioxide, matter rearranged, energy released. In the same way, the effort of learning transforms, never wasted, always moving forward into something new. And so, the candle connects us to a long tradition. From alchemists searching for hidden truths, to Boyle testing the air, to Lavoisier weighing reactions, to Faraday inspiring children, the candle has been a silent witness to the growth of science. Its flame-lit manuscripts, illuminated microscopes, heated experiments, and guided discoveries that shaped the modern world. Even now, when laboratories blaze with electric light and instruments hum with precision, the candle reminds us where it all began. Perhaps this is why we still light candles in moments of reflection. Their glow invites quiet, focus, thought. To watch a candle burn is to remember that even the smallest light can reveal mysteries. In its steady flame is the essence of science itself. Fragile, fleeting, but endlessly capable of illuminating the dark. So as we come to the end of this journey through wax, flame, and history, we return to the simple image with which Faraday began. a candle burning on a table, a flame rising into still air. It is ordinary, and yet it is everything, a universe contained in a single glow.